research. It's a collaboration between the Air Force Research Laboratory's Sensors Director and Human Effectiveness Director, as well as the University of Dayton. So I'm from the Sensors Director, and Chris is from the University of Dayton. And the objective of our research was the development of 2 cognitive agents that take in sensor data from cameras, such as a spiking camera or EO camera, and processes it on a low-E neuromorphic device in order to develop a low size, weight, and power, real-time autonomous solution. We have two cognitive agents. The first one is CSEP, which stands for Cognitively Enhanced Complex Event Processing. What this is, it's a net-centric framework that takes in high-level mission requirements and the current situational data in order to make planning decisions. And then the second cognitive agent is what we term as NeuroSPA, which is SPA stands for Semantic Pointer Architecture. And what it is it's a neurocognitive-based model for knowledge, representation, and reasoning. So I'll be talking about the NeuroSPA agent, and then Chris will later on talk about the CSEP agent. So the NeuroSPA agent, what it really does is it takes in perception, so it identifies objects in the scene, whether it's in a virtual scene, such as VREP, or the actual scene, and it uses these objects as input to a reasoner, which then decides on a course of action for the robot to take. We based our reasoner off of a Bayesian belief network that was developed in Problem. And what we wanted to do, though, was develop it on a dynamic bio-inspired neuron components. So what we were doing is we're building it via NANGA from Applied Brain Research. So some of the things that we were most interested with NANGA was that it's semantic pointer architecture for representation, as well as the basal ganglia and thalamus components of NANGA for the action selection. So we were able to develop an initial reasoner. It was more of a reactive robot. And so our first initial implementation, it identifies objects in the scene using a convolutional neural network, and then maps it to 3 different moods, so hunger, fear, and curiosity. And then using those moods, as input into the action selection, it determines what action for the robot to take. And for our case, it decides to either feed, flee, or explore. And we're able to successfully get this running. But in the future, what we would like to do is add more complex components to the reasoner. So for example, we would like to incorporate spatial reasoning and memory so that as it's going along, it's able to remember what it's seen and be able to perform more complex reasoning based off of that. And then I'll let Chris talk about the CSEP.
Yeah, so the CSEP agent is an autonomous decision-making structure that commonly tries to find the best course of action within a wide solution space. And sometimes that can get very power and time-consuming, so we're looking at low swap options. And this is one of our approaches we looked at, this neuromorphic option. So we are doing things with asset allocation and tasking vehicles to targets in the best possible way. And you can see that the number of possible solutions as problem size increases so rapidly that something that's doing an exhaustive search just gets too weighed down by it. So I guess I was looking into ways to fix this, and we started with a spiking algorithm. And this is one example output, and it would just be a system that spikes, that then relates a set of vehicles to a set of targets. And this is a little bit about what the algorithm's doing. So if there's a grid of neurons that each one represents a connection between a vehicle and a target, and then there's different types of feedback control. The neurons integrate according to target priority, target time, and then target completion time, and then a probability of success. So those terms are in the feedback, so then we have a vehicle and target control based on which neurons are firing. And if a vehicle gets to a target, we assume all neurons associated with that vehicle are shut off, and then we end up with a allocation based on importance. And that's a little bit about what the neuron map might look like, different inputs according to those parameters. And here's a scenario simulation. So we have a connectivity matrix to hold compatibility. So vehicle 3 isn't appropriate for target 5, so there's no neuron integrating. Vehicle control stops a vehicle from being a possibility if a vehicle is already allocated somewhere else, like in the target for vehicle 3 situation. And then there's also a target control, so all the vehicles don't go to the most important target. Vehicles are penalized after one target has already been assigned. And these are some quick results. So we can do this very fast and with very low power, but we can only do about 99.9% optimal solutions as opposed to the GPU that can do 100% right every time. But as the GPU scales further and further, it's just not possible to do, so we're looking at these alternatives. And this is a quick timing comparison. Now, these results are just based on a MATLAB script. As of last week, we were able to get this information running and through processed. So we were looking at doing this on a Luihi system, and we can do an 8x8 allocation on a Luihi in less than a millisecond, which was pretty good. And then we have very significant speedups here because we're comparing a GPU search to this alternative algorithm. And if we run this same algorithm on Intel or Asus Tinkerboard, we can get a speed up on the Luihi of about 10 to 20 times and a power efficiency of about the same. And that's okay. It's not the 10,000 times that some of the algorithms do, but we're also only using 100 neurons. So we think as we scale these systems up, the traditional looping architecture is going to get stressed more and more, and the Luihi is going to continue to work in this parallel system. And we have a spiking solution that scales according to problem size and not solution space anymore. So everything's going pretty well right now. These are where our results are published so far. We'll present the Luihi results at IJCNN in a couple months. And from here, I think we're going to look at maybe constraint satisfaction and seeing how we can broaden this example.
Thank you, Chris. Harshit?